Good evening, everyone. I'm Anish Ambekar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. Welcome to this week's live interaction for the NPTEL course, Dynamic Behavior of Materials. The course code is NOC24 ME102, and this session is part of the week 5 lectures. So, in this fifth week, we have first looked at Wilkins-Guinan analysis for the Taylor test. Taylor test, if you remember, it's for impact of finite rod on a rigid plate, and then from that we try to infer what the dynamic yield strength for the given material looks like. Then we moved into shock waves, a basic introduction of the scene, and finally moving into the Rankine-Hugenoid treatment. So we have already seen in previous lecture about Taylor's test. Suppose this is my finite bar, some initial velocity u, and it hits a rigid boundary. Then what happens is the bar ends up getting deformed with some plastic deformation near the rigid boundary. In Taylor's analysis, we have assumed like there is a distinct in Taylor's analysis. We assumed a distinct plastic front, moving plastic front. However, in the Wilkins-Guinan analysis, there are a couple of things that we have to note. So before that, I should write down the limitations of Taylor's analysis. So the first one was uh, the deformation could have some mushrooming at high speeds. So it's not conical in a sense. The another part was this boundary elastic elastic plastic boundary wasn't very distinct. So you couldn't easily differentiate simply by looking at a sample what is happening. So what Wilkins and Guinan did was they performed similar experiments, and they also involved some computational code to try and study what happens inside this finite bar impacting a rigid surface. From that, they found a few things. They found that first was that this reduction ratio, which is LF by L naught, was independent of the original length L naught. So if I have to plot it, LF by L naught versus this impact velocity, then they observed something like this. This is zero impact. This is uh, at zero velocity, same. There is no reduction in length. Another thing that they noticed was they noticed that plastic front. So when what is plastic front? So when the bar impacts the rigid surface, it will start deforming. So there will be some material will flow radially outward. There will be something like this will be the plastic front wherein the material has started flowing, started undergoing some permanent deformation. What they observed was that this plastic front was very close to the rigid surface, and could be effectively, which meant that we could effectively consider the rigid surface, rigid wall as the start of plastic film. So it's the second part. I think a little more uh, discussion is required. When the bar impacts the rigid surface, uh, stresses are generated, and that will cause some elastic wave to move to the free end, opposite end of the bar. If that stress exceeds elastic limit, the material will undergo plastic deformation. So part of the material will start moving radially outwards, and the portion or the length of the rod which will be undergoing this plastic deformation, it will be, uh, I'll suppose I denote this as H. This H will be typically small compared to L naught. So what Wilkins and Guinan first did was they assumed that the very first assumption was uh, the rigid surface and the plastic front are at almost the same location. When they did so, so assumption, rigid surface is almost same location as plastic front. From this you basically get that your instantaneous decrease in bar length is proportional to impact velocity. So which is basically saying dl is minus u times dt. Dl is the change in length, the bar. So you could write dl by dt is equal to minus u. So this is the first equation. Another equation we get from using Newton's second law. We get force is equal to mass times acceleration, which is, if we assume at the, sorry, because the bar is being plastically deformed at this end, we can take the stress that the bar experiences to be the dynamic yield stress. So your dynamic yield stress times area can be written as rho rho naught L being the instantaneous length, A being the current area, into acceleration. So acceleration is du by dt. If I move this around, what I get is sigma yd is minus rho naught L du. 1 by dt is nothing but 1 by dt is minus u by dl, minus u by dl, which gives us dl by L is equal to rho naught sigma yd u du. If I integrate this, L naught to Lf and u going from u to 0, I get log of final length by initial length is equal to minus rho naught. This should be rho naught by sigma yd. Sorry, rho naught u square by 2 sigma yd. So this is the third equation. So what they did was they used this to evaluate how the dynamic yield stress looks like, and what they observed was this relation where Lf is equal to L naught exponent of rho naught u square by 2 sigma yd. This equation, rather this exponential nature of this equation matched well with observations. So they still haven't arrived at like the final equation, but they were able to see that okay, this sort of form where final length is initial length times e raised to minus u square by sigma yd. This final form of equation matches well with what we are seeing in reality. So they went a step ahead and then they did another observation. So experimental observation. Another observation that they did was size of plastically deformed material or plastically deformed material zone. Suppose I write it as H. H. I'll show it here like this. This thing is H. This is the current L, length L. This is area A. Right. So this size of the plastically deformed material zone is independent of impact velocity, which gives us H by L naught. We can treat it as a constant. So if we go back to our previous derivation, we have seen that H, this is the plastic front, and here the stress value is sigma yd, which is dynamic yield stress. So we basically go through the same equation as before, but instead of uh, H less than L naught, where we have H by L naught equal to constant. So the value that they have reported in their paper is I think 0.08. So it's still low, but it will play some sort of effect on the final. It will still have some effect on the final equation. So when we went from dl by L is equal to rho naught u square by rho naught u du by sigma yd. This was our equation. If we integrate this, now we change the limits to go from L naught minus h to Lf minus h. So what we are saying is at the moment of impact, within a very small amount of time, the material up to length h will be plastically deformed, and after that there will be no more other rather there will be negligible increase in the plastic deformation zone h. So my total like that length between free surface and plastic front goes from L naught minus h to Lf minus h, as my velocity of impact goes from u to 0. Once I put in these equations, I get Lf minus h is equal to L naught minus h into exponential of minus rho u square twice of sigma yd. So if I rearrange this equation, I get Lf minus L naught is equal to 1 minus h by L naught exponent minus rho u square by 2 sigma yd plus h by L naught. So this is what the final equation ends up looking like. If I draw LF by L naught and rho u square by 2 sigma right, it will go from say 1 to a point decreasing. So this model curve matches very well with aluminum, iron, tantalum, and so on. I think even uranium there. So this Wilkins-Guerin analysis basically is a more better is a better model rather of the same phenomenon. Okay, and from this equation, what you can think of now is suppose I have measured L naught, I have measured what the final length looks like. I know my plastically deformed region as well as my density and impact velocity parameters. Then from that, I can estimate what my dynamic yield strength looks like. So transition from elastic to plastic region. This analysis has been shown to hold well for high strain rates, so like up to 10 raised to 5 per second of strain rate values also. We have seen that this analysis works well. Okay, so the next part in this week was introduction of shock waves. So moving from elastic waves, then plastic waves, and now into shock waves. So if you, what is the condition for a shock is there should be like a sudden release of, there are a few conditions, but we'll go through it. So suppose you have something like an explosion, right? This involves a sudden release of energy, and we require a certain condition between wave velocity and pressure. If there is a sudden irreversible process, like a large release of energy in a very short duration, there is some media to transmit it, which has this condition that the wave velocity will increase with pressure. Then you have a very thin shock front being created, which uh, which is basically your shock wave, and it cannot. It requires a medium, so it cannot propagate through vacuum. So if I want to differentiate between sound waves and shock waves, sound waves are usually small amplitude compression waves, whereas shock waves are finite amplitude waves. Another thing about sound waves is it has like a basically sound speed itself. I'll write it here, and this has a higher speed than sound at whatever local temperature it is. So because of the sudden release of energy, there will also be an increase in temperature. Third is after sound wave passes through, so the third condition is after sound wave will pass through, material state is unchanged. Whereas when shock wave passes, material will generally be at a high temperature pressure state. Later on, we'll see that this could also result into like say, phase transformations and so on. There is a lot of history going into the research of shock waves. The pioneering work probably comes from Rankin and Huguenot, which we'll be looking at in detail. But there have been other important contributions, including Rayleigh and Stokes, Rayman. Important thing about like dealing with this is we have for our analysis we have conservation equations for analysis. We'll rely on conservation equations. So separately for mass, momentum, and energy. So these are fundamental laws which we'll be looking at. And when doing so, we typically ignore heat conduction. So because there will be an increase in temperature locally, there could be some sort of heat conduction. There could also be, say, viscous effects. We do not take this into account in our simplistic analysis. So this sort of thing basically feeds into what could be adiabatic and reversible thermodynamics when we say ignore the heat conduction and viscous effects. If we look at say a sound wave, C square is proportional to pressure for the case of gas. It will be proportional to for the case of solids we know that C square in solids is proportional to dou sig d sigma by d epsilon at a given epsilon. Similarly, for gases, it's proportional to pressure or a specific volume at a particular given volume. This would give you the local sound speed. So now coming back to the important condition. So the condition is as pressure increases, your sound wave velocity or wave velocity, I'll write it as u, should also increase. This is the important. If think about it in another manner, if with increasing pressure there is a decrease in velocity, then what we would have is as the compression moves forward for higher pressure, your velocity will slow down, and then those different components will move at different speeds. That is basically dispersion. Like at different pressures, you will have different wave velocities. If if the wave velocity decreases, then you would have with increase in pressure, then you would have the higher pressure component moving slower, lower pressure component moving faster, and with time the lower pressure component will move far ahead, whereas the higher pressure component is yet to reach. So whatever wave or whatever pressure pulse that you have, that will slowly start widening if this condition is not satisfied. When this condition is satisfied, we'll have a picture that looks like this. Suppose I draw pressure and it's my Cp at T is equal to T1. Suppose this is how my wave looks like. If this pressure amplitude is sufficiently high, then I know that I have different wave speeds, say C here at the mean, C minus delta C at the bottom, and C plus delta C at top. So different pressure components will move at different speeds. So as we move from time t equal to t1 to time t equal to t2, you will have this is c plus delta c, this is c, this is c minus delta c. T is equal to t2. If I go one step ahead, t is equal to t3, you may even have an inversion of sorts. This inversion is unphysical. So this inversion is unphysical because it gives multiple pressure values for same location. So that is not possible because physically at any given point with at any given instant of time you'll only have one pressure value. It may change with time, or it may even change as you move around in the material, like with x, but at a given x and at a given t, you should always have only one pressure volume. So what happens in reality is, so in reality, what we end up with is steel, steel shock front, right? So you have single value of pressure at a given x. If you look at it microscopically, what we have is there are large gradients in temperature and velocity at the front of the wave. And these cause irreversible irreversible process. Irreversible because there will be some sort of heat conduction viscosity involved. This these irreversible process are dominant in the thin shock. Why they are dominant there? Because again, it's due to the large gradients. Because of the large gradients, whatever heat conduction and so on has to happen, as well as large gradient in velocity, whatever viscosity effects have to be seen, those will be much more pronounced at the shock front itself. Macroscopically, you have conservation of mass, energy, and momentum. So, when I say conservation of energy, that also involves, say, the amount of energy that goes away, that would go away into, say, viscous loss. For modeling purposes, we'll be not looking into those. We'll be looking at only, say, the energy of uh, the material itself, like the internal energy and the kinetic energy. And if I draw a thermodynamic diagram, suppose this is point 1, this just behind the shock is point 2, and this is point 3. This is say pressure specific volume. This is entropy state 1, entropy at state 2. So you have say state 1, then it will go to say a state 2. From there on, it will go to a state 3. So from 2 to 3, there is a adiabatic uh, passage of the shock wave, whereas from 1 to 2, you would have non-adiabatic uh, transition of state. Important thing to note is that this is a very small, the shock front is very thin, and that basically means that macroscopically when we are modeling, we will treat it as like a discontinuity in pressure right before and after the shock front. And okay, so as I mentioned at the beginning, sudden release of energy in a very short duration could be say mechanical or chemical and so on. So third part was related to the Rankine UV node treatment. So we are doing a hydrodynamic treatment. So like similar to how this phenomenon is modeled in the cases of gases and fluids. So we have a few assumptions that I'll write down. Shock is a very thin discontinuous surface. There is effective shear modulus. Mu is zero, which basically means that our material behaves as a fluid. So because the normal stress say is so high, there is a state of uniaxial strain generated. There is no lateral flow, and you can effectively consider uh, material to have like no shear modulus. The dominant phenomena is only the normal pressure that was applied to high amount of rudder pressure that was applied to develop a shock front moving inside the material. We'll ignore body forces and heat conduction and viscosity. So we'll also ignore so like no phase transformation. This will study I think in week 7 or 8 I think how shock can also lead to phase transformation and how it is used in the industry. And we are also have no elastoplastic behavior. So very simplistic. So these assumptions basically make our life very easier, much easier. The fundamental requirement is that as pressure increases, wave velocity also increases. So if these conditions are satisfied, you can get a shock front inside a material. And if now we have to analyze it, I'll just draw a simple diagram. This is pressure. This is X. This is the shock front. We'll call this region behind the shock front and we'll call this ahead of the shock front. The shock front will move with some velocity us. Ahead, the material has properties rho naught, internal energy E naught, velocity u naught, particle velocity, and behind you have particle velocity up, density rho, pressure P, internal energy E. Here, pressure is P naught. So, this is the diagram. So, the first equation is conservation of mass. We can do this by constructing, say, a small control volume right ahead and behind of the shop front, very thin, just ahead and just behind. Then you can see that there is some material flow entering this control volume with an apparent velocity of us minus u naught, and then there is also some material flow exiting the control volume with an apparent with a relative velocity us minus up, right? So if I take small time dt, you have mass in equals mass out. There is no source or sink for the mass to go anywhere, so mass in has to be equal to mass out. And mass in you can write rho naught into area A of the control volume into us minus u naught dt is equal to rho A us minus up into dt. Cancelling out the area and time terms, you get an equation which is rho naught us minus u naught is equal to rho times us minus up. This is the first equation. Generally, you have u naught equal to 0, so I can rewrite this as rho naught us is rho times us minus up. And write this as equation 1a. Second equation is conservation of momentum. Again, we'll look back at our uh, small control volume before and after, sorry, behind and ahead of the shock. What we see is that if we have, say, a small, I draw these two rectangles. This I'll call, sorry, rectangle ahead, and this I'll call rectangle behind or region behind. Region ahead had some momentum, so momentum of region ahead plus the impulse that was provided gives me the momentum of. I'm writing this as a vector so as to avoid any confusion with pressure. Next was conservation of momentum. As the small region RA crosses the shock front, it experiences pressure P, which is higher than pressure P naught. That leads to the difference in pressure. Basically, can be thought of as a difference in force leading to an impulse over the small time dt. That impulse gives us change in momentum for that small region. So if I have my change in momentum equals impulse. So my final momentum is rho A us minus up, so into dt, which is basically my dm into my particle velocity up, particle velocity minus rho naught A US minus U naught dt, again the same mass with an initial velocity U naught equaling the impulse. Impulse is nothing but my total force being applied into time t. So change in pressure into A into dt. If I remove the uh, area and dt terms, what I end up with is rho naught rho US minus UP. I can write rho naught US minus U naught. This rho US minus UP. I can write rho naught US minus U naught into UP minus U naught is P minus P naught, which is my equation 2. And from this, if U naught is 0, which means initially the material is stationary, you have rho US UP is P minus P naught. It's equation 2a. From if you recall, this equation 2a looks pretty similar to the sonic impedance equations that we have studied in week 2's lecture. So I can write a term called as shock impedance given by rho US, similar to the sonic impedance that we have seen earlier. My third equation is conservation of energy. This will give us that external work done on the system is equal to change in internal energy is change in kinetic energy. External work done, this is nothing but uh, this is found by the pressure differential that we are applying. Here, I think I should mention that in this diagram, right? I should mention here in this diagram that whatever this material that we have behind the shock front, right? It usually doesn't have like the same state of stress and same rho and same E throughout that we have assumed as rho, P and E and particle velocity OP. There is some change going on between here and there, but what we essentially assume is that in this type of model we assume that our density, pressure and internal energy, particle, all those things are constant behind the shock front. They do not vary at different locations, which is how it is in reality. When I come back to the work done, I will then be using the constant pressure P and what the constant pressure P multiplied by the area A to give me the force. So P into A, which will give me the force, into the distance this force acts. So this force acts for a distance UP into dt, which is so P pressure, A area force acting on that small each particle, small thin cross section UP dt minus the same thing ahead of the shock front. So you have got P naught A into U naught dt. If I write change in internal energy and change in kinetic energy, it's nothing but half rho A UP minus US minus UP into dt, which is your dm into UP square plus E. E is the internal energy per unit mass into rho A US minus UP dt. So this is my final internal energy plus kinetic energy minus half rho naught A US minus U naught dt U naught square plus I should write this E1 plus E naught rho A US minus U naught into dt. If we take U naught equal to 0, you have P into UP from the from this equation. I'll cancel out A and dt terms is equal to half rho US minus UP into UP square plus E1 minus E naught. These two terms are essentially my dm terms to dm. So dm, as we saw, was rho naught US minus u naught rho naught US. Again, this can also be replaced by rho naught US. So you have P into UP being rho naught US times half UP square plus E minus E naught. This is equation 3. This is the conservation of energy equation. So if I write down all three equations, for U naught equaling 0, you have rho naught U naught is equal to rho US minus UP. Conservation of mass, conservation of momentum gives us P minus P naught is rho naught US UP. And finally, you have conservation of energy gain. P into UP is equal to rho naught US square. Sorry, rho naught US into half UP square plus E1 minus E minus E naught. Okay, so here we can see that we can say measure rho naught and P naught and E naught, which are the initial states. So rho naught, P naught, E naught, initial states. These are measurable, which gives us rho, US, UP, P, and E as the unknown variables. Since we have five unknowns and three unknowns and three equations, we end up with we'll end up with, say, a surface, which means that it may not be possible to deterministically know. Like, say, suppose you have rho US and UPR measures, then you will have a locus of points for pressure P and internal energy E, which will span a surface. So there will be no like the locus of final shock state will have a series of points which may not be easy to decipher from. Like, you'll have much more number of possible states, just so to speak. We'll leave it here for now. Well, one thing we can do is we can rewrite our conservation energy equation as E minus E naught is equal to P UP upon rho naught US minus half UP square. So if we look back at our conservation equation, conservation of energy equation, we have E minus E naught. We can rewrite it as P into UP upon rho naught US minus half UP square. If we write UP is equal to E minus P naught upon rho naught US, then you have E minus E naught is equal to P times E minus P naught upon rho naught square US square minus half P minus P naught whole square upon rho naught square US square. Right, so this gives us, again, if you use conservation of mass, you have rho naught minus rho into US is equal to minus rho UP, which is minus rho P minus P naught upon rho naught US. So you end up with rho naught US square is minus rho P minus P naught minus P naught into 1 by rho naught minus rho. Writing this in terms of specific volumes, 1 by rho is equal to P, and simplifying you get rho naught square US square P minus P naught upon V naught minus V. And if you substitute this equation back into this equation, you end up getting E minus E naught is P times P minus P naught into V minus V naught minus V upon P minus P naught minus half P minus P naught whole square P minus P naught V naught minus V, which gives E minus E naught is equal to half of P plus P naught V naught minus V. So this is the more common form of conservation of energy equation. So as mentioned, we still have locus which is two dimensional. To restrict it further, we use something called as the equation of state, which is like a relationship between shock and particle velocities. So you write shock velocity is c naught s1 up s2 up square and so on and so forth. Here the coefficients S1, S2 are basically your empirical parameters which can be measured. For most metals, you have S2 being 0, so you can write US is equal to C naught plus S1 UP. We call this as equation 5, this as 6, this block as equation 4. So what if I have to draw shock versus particle velocity? You have something like this for iron, something slightly different. These are all straight lines by the way. For copper, you also have something for which is almost a straight line for NaCl cable salt. You have at higher velocities you have chromium and so on. So the exact values of these parameters can be found in a number of references, including one by Mayers and Moore. And this relationship not for porous materials, linear relationship, and also not for phase transformation. Right. So once we have all this plugged in, we can draw a locus of points for a shock state. If I draw this in a particular axis, which is pressure and V by V naught or a specific volume, suppose the initial pressure is P naught, initial volume is V naught. So this is my starting point. I get a locus of point. Let's look like this. This is the Rankine or rather also only known as the Huguenot curve, which is a relation, which is a locus of all possible shock states from a given state P naught V naught using like the block of equations 4 equation of state 6. So from this, we get locus to be a single straight line. Sorry, not straight line, a single line locus. So we'll learn more about this Huguenot curve and Rayleigh line, I think, in the next session. So yeah. This doesn't mean that if suppose my final state is P1 V1, my initial state is P naught V naught, it doesn't mean that my material will travel along this line. This is wrong. What happens is basically the material jumps from this state to this state. So if you remember the diagram for pressure, this is distance you had. This is ahead of the shock front. This is behind the shock front. Right behind, right ahead. So there is a quick jump in a very short amount of time. Okay. Right. I also can show pressure versus particle velocity plots. They look like, suppose this is tungsten, this is uranium. So this is in GPA usually. Kilometers. So with increasing pressure, uh, particle velocities increase. So suppose you have copper, right? If I write pressure, density, specific volume ratio, shock wave speed, and so the particle velocity. At zero, you have 8.93. This is gram per cc. This is GPA. These velocities are both in kilometer per second. No change in specific volume. 3.940, very little particle velocity. So if, if you jump to 10 GPA, the density suddenly increases to 9.45. There is a decrease in specific volume. Shock velocity is now distinct and larger than your sound wave velocity. There is a substantial particle velocity involved. Suppose I jump to say 20 GPA, there is further increase in density, further decrease in specific volume, further increase in the shock wave speed, and a much larger particle velocity. So this trend basically continues. You have like a whole series of shockwave parameters in tabular form as well as these graphical forms provided in the textbook as well as for this equation of state. So if you are interested, you could go into them specifically. Okay, I think this is what was covered in this week's lecture. If you have any doubts regarding the same, you may voice them now. If not, then we can call it a day. I think I finished a little early today. Okay, then thank you. I guess this is it. Thank you, and I'll see you again in the next lecture.